Hi guys, so my group which consists of Chima, Mario and me, for a wave inquiry lab, we had to analyze beat frequencies and different patterns in mono tuning forks. So the main question in a wave inquiry lab was, what are beats? Beats are regular pulsing of the loudness of a sound which is produced when two sources produce sound of slightly different frequency. So the tuning forks provided to us on Woodstock are kind of worn out over a period of 40 years, and when struck they produce a sound which has a frequency of 30 Hz above or below the actual frequency. So for our wave inquiry lab we investigated tuning forks of 320 Hz, and to calculate the beats we had to investigate them separately, and these are the results we got. So to calculate the frequency we had to calculate the number of waves in a given area, and the time difference was shown by delta t in logger pro. And for example, if delta t is 0.5 seconds and the number of waves is 2, so to calculate the frequency you divide the number of waves, which is 2, but the difference in time is 0.5, which is the same as 4 upon 1, which is basically saying you are expected to see 4 waves in 1 second. So once we got different frequencies for both the tuning forks, to calculate the expected beats we should get is through the formula F2, which is 329.7 Hz, minus F1, which is 332.1 Hz in our common data, an absolute value which was 2.4 Hz. That means we should be able to see slightly above 2 beats in 1 second. So according to our data, we should be getting slightly above 2 beats, and as you can see, it's kind of sketchy and not really clear. But then we did get 2 beats, and then in the front and later you can see half or like 0.2 of beats, which makes it like slightly above 2 beats.
Why exactly is it that tuning forks have 2 prongs?
Tuning forks should have 2 prongs as they are meant to move in a uniform and balanced manner. However, if there was only one prong, the oscillation energy of the tuning fork would easily get transferred to the hands of the user. This process would happen fairly fast and would mean that the sounds, vibrations created by the tuning fork would not last.
Do tuning forks have a pure sound?
A pure sound is a sound that can be graphed as a sine curve. Tuning forks do, in theory, and while making a few assumptions, have a pure sound. These assumptions include assuming that a tuning fork makes a sound of only one frequency and assuming that it doesn't lose its oscillation energy. This is true in the sense that the graph produced by the vibration patterns of a tuning fork whose energy doesn't run out, and one who plays only one frequency, will have the same shape and pattern as a sine graph. The reason that the assumptions are made is to ensure that no other waves, ones of different frequencies, interfere, effectively changing the shape and pattern of the graph. However, should this assumption be met, the graph will that of a sinusoid. The amplitude of the graph remains the same, as the amplitude represents both the volume of the sound itself as well as the energy of the mentioned wave.
Can adding a piece of plasticine to the tuning forks change their frequencies?
Yes, it can. This is because assuming there is a constant amount of energy supplied, the extra mass of the plasticine will take up more energy to move when compared to the tuning fork by itself. This requirement of more energy will mean that the frequency produced will be lower than the original one.
Can you fix the frequencies of tuning forks, that is, return them to their original frequencies?
This can, in theory, be done in a variety of ways. One of the ways this outcome can be achieved as mentioned in the question above, some plasticine can be added to the tuning forks to change their current frequencies, although this will have to be done by a lot of trial and error.